Sorry, did everyone get one of these handouts? You need one? Okay. Okay, so we're going to continue on this idea of, we have some question. Does, is one group more likely to have this than the other group? Okay, or, is one group more likely to be this than the other group? So we ask things like, are the females more likely to have survived than the males on the Titanic? Or is the Northeast region more likely to be Republican than the other regions? Okay, so we have a general question like that, and in order to truly answer that question, we would need to survey everyone. Okay, so here, the example I provide on this paper says, do a greater percentage of men, I wrote watch and read the news than women, but let's, scratch out the word watch, should have been read. Okay, so do greater percentage of men read the news than women? Okay, I don't know the answer to that. Okay, and the only way we could truly answer this question is if we survey everybody and we find the percentage of men who read the news and we find the percentage of women who read the news. Okay, but this would require us to survey everyone. Let's say we would just want to know for the United States. There's 300-something million people in the U.S., and we'd have to survey all of them and say, are you a man? Are you a woman? Do you read the news? Yes or no? Okay. And that would be a lot of work to survey every single person, right? It's not going to be possible. Okay. And so that's what this paragraph says, okay? To get the true percentage of men who read the news, okay, we need information about every single man and whether he reads the news or not, okay? And the same goes for women. So we would need to get the true percentage of women who read the news, we'd need to survey every single woman and ask whether you read the news or not, okay? And that's like 100-something million people to survey. That's too many people to ask, okay? So we can do something called statistical inference, and this is where, in my opinion, statistics gets exciting in that we don't have to survey 300 million people, okay? We don't even have to survey 1 million people. We can survey just a couple hundred people, okay? And based on the results of a couple hundred people, we can start to answer a question. Check the homeworks. Okay, so we need to. We don't have to survey all 100 million people. We can just survey just a couple hundred people, okay? And we can still get an idea of the answer to this question, okay? And so this saves us a lot of energy, right? It's much easier to survey just 200 people than it is to survey 100 million, right? And if we can survey just 200 people, we might be able to answer the question. There's just, but now that we're using only 200 people, there's what we call sampling error, meaning that the fact that I'm picking just a small number of people, 200 or something like that, this might not be truly representative of the population, okay? So these 200 men that I'm choosing, I'm hoping represents all men in the United States, but it might not, okay? And I'm picking these at random, okay? And by picking them at random, it should be kind of representative of all men. But because it is random, there's always the possibility that it's not truly representative. Okay, so I'm going to just do a little demo here. Okay, I have 2 decks of cards, and I can just randomly select, let's say, 10 cards, okay? Now, I'll tell you that this deck is a fair deck. Half the cards are red, half the cards are black, okay? Now, if I select 10 cards at random, how many are going to be red and how many are going to be black? So I'm selecting 10 cards at random out of... Okay, so we're expecting 5 red and 5 black, or we're expecting something around there, but we also know because I shuffled these and these are randomly selected, I might not necessarily get exactly 5 red and 5 black, right? So I'm going to just flip over 10 cards, okay? So we got 1 black, 2 blacks, 1 red, so I'm going to just flip over 10 cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So I flipped over 10 cards. 4 of them were black and 6 are red. Okay? And that seems reasonable. Okay? We didn't get exactly 5 red and 5 black. We got 6 red and 4 black. Okay? So that was one survey result. Okay? Okay, so let's just say we got 6 red and 4 black. Okay, so that was one sample, and I can shuffle the cards again. You're supposed to shuffle them 7 times to get them truly random, but I feel like that's a lot of shuffling here. But okay, and then so I'm going to just do another 10 cards. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this time I got 5 red, 5 black. Okay, so that's exactly how I expected. Okay. Okay, and we can do this over and over and over again. Okay, and I'll spare you the pain of that. But is it would you be shocked if we got 8 red and 2 black?
No.
No, that's not shocking, right?
No.
Okay. It would be like, oh, well, that doesn't happen all the time, but it could happen, right? And so, because here we're only looking at 10 cards, we're expecting, our brain says, you know what, because these are just randomly selected cards, our brain has an idea of that we can't always expect exactly 5 red and 5 black. Okay, so even though the deck, all 52 cards, if I looked at all of them, exactly half are red and exactly half are black, whenever I pick 10 random cards, I'm not expecting to get exactly half red and half black, okay? I'm expecting something around there, but something a little bit different from that is not completely shocking to me, okay? So, in the deck, exactly half are red and half are black. But because I select cards at random, I'm not expecting my cards to always be exactly half red and half black. And so we have to kind of, we're accustomed to this kind of thinking or expectation when it comes to selecting cards from a deck, okay? But the same kind of thinking has to be applied and generalized to large surveys also, okay? So if I select 200 men and 200 women, the men that I select and the women I select may not necessarily reflect exactly what the entire population looks like, okay? And so let's say I surveyed 200 men and 200 women, and I asked these men, what percentage of you read the news? And I asked the women, what percentage of you read the news, okay? And let's say, and I'm totally making up numbers here. I have no idea what the numbers are. But let's say 70% of the men read the news and 65% of the women read the news. Okay, these are the 200 people I asked, 200 men, 200 women. 70% of the men said I read the news, 65% of the women say I read the news. Does that mean, so I'm getting a 5 percentage point difference between the men who read the news and the women who read the news? Okay, is that okay with me so far? So let's, I'm going to just write this down, just make sure we're on board here. Okay, so this is pretend survey. Oops. Okay, we asked 200 men and 200 women, and I happen to ask the same number of men and women, but that's not even required. Okay, and let's say in our pretend survey, 200 men, 200 women, these are randomly selected people. Let's say 70% read the news and 65% read the news. Okay, so I have a 5 percentage point difference between these two sides. Okay, 65% over here versus 70% over here. Does this then indicate that if I were to survey all men and all women, that I would see more men reading the news than women? Well, and so the answer is maybe, maybe not, okay? Right now we feel like 5 percentage points. If you're saying no, in your brain you're saying 5 percentage points is not a really big deal. So that difference could be attributed just to the fact that these people were selected randomly. That's probably what you're saying in your brain. On the other hand, okay, so if you say, so one line of thinking is 5 percentage points is not a big difference. This can be attributed, this difference can be attributed to random sampling. Okay, and so the technical terminology here is this difference is statistically insignificant. Okay, does that feel okay? so far? Yes, no, maybe. On the other hand, let's say it turns out 90% of the men I surveyed read the news, and 20% of the women read the news. Okay? So maybe this isn't the US, maybe this is another country or something. Okay? We don't know. All right? So let's say 90% of the men read the news, 20% of the women read the news. Okay? What kind of difference am I seeing there then? I'm seeing a 70 percentage point difference. Okay? And probably if we see a excuse me, my throat's all getting messed up here. If we see a 70 percentage point difference, we're not going to say, oh, that's just a result of the fact that we picked people at random. Okay? It probably reflects that something is going on so that fewer women are reading the news and more men are reading the news, whatever it might be. Okay? Maybe this is a place where women are oppressed or they're, we don't know. Okay? So in that case, we would say this is a large difference. This difference is statistically significant. Okay? So let me just, so I'm going to write that. Okay? Just want to make sure we're still with me. Okay, so another pretend survey. In another country. Okay? People randomly selected. Okay, we'll say 200 men, 200 women. Okay, 90% read the news, and over here, 20% read the news. Okay, so now we have a 70 percentage point difference. Okay, and we would say this difference is large. The 70 percentage point difference is big. Okay, and we would say this difference is statistically significant. Okay, and this tells me that if I surveyed everyone, all men and all women, I would find a greater percentage of men reading the news than women. Okay. Now I'll let you guys finish writing. Just want to make sure we understand this concept here. Okay, so in the previous slide, we said a 5 percentage point difference, that doesn't seem very big. It could be just a result of the fact that I picked these people at random, right? Because if I took another survey of 200 men, I'm not going to get exactly 70% reading the news. Maybe I get 68% reading the news. And if I took another survey of women, maybe I also get 68% of the women reading the news. And in that case, there's no difference between the number of men and women who read the news. Okay? So over here we're saying this 5 percentage point difference doesn't seem like a big deal, especially if we take into account that these people were selected randomly. Okay, just like I'm dealing out the cards at random, we're expecting some amount of variation there, right? But over here, when I get 200 men and 200 women, I'm getting 90% reading the news and 20% reading the news for the two different groups. That feels like, you know what, that can't be just from random selection alone. That probably reflects something happening where whatever it might be, we're not trying to answer questions as to why, but does this mean more men read the news than women in this place? It would seem so, right? A 70 percentage point difference we can't just dismiss. Okay, do you have a question?
Which percent is considered?
Exactly. So the question is, when do we say a percentage point difference is significant or not, right? So if we got a 25 percentage point difference, is that significant or not? A 15 percentage point difference, is that significant or not? Okay, so to decide the line between what's significant and what's not significant, there's some calculations are involved, okay? And, you know, the first time you see these calculations, it's going to feel like, oh my gosh, I have no idea where these numbers are coming from. The first couple times, it's going to feel uncomfortable, and you're probably not going to like it, but when you do it a few times, I think you'll get the hang of it, okay? But there's some number, right? When we say this percentage point difference is significant and this one is not, okay? And it depends on all sorts of different things. I can't just say this percentage, if you see this percentage point difference, and that means it's significant, okay? Because it depends on how many people are surveyed and things like that, right? So if you survey 1 million people, a percentage point difference of like 0.5% is going to be significant. But if you survey 200 people, you're going to need a larger difference, right? Okay. Just because with 1 million people, you're getting a much probably better representation of what the population looks like, right? So we're going to get into these calculations. So first, I'm going to label a generic table, okay, with A's and B's and X's and Y's. And so if you never taken algebra or you're not used to seeing things represented symbolically, it might feel kind of awful. But, you know, there's just, there's no way to represent every single situation without using symbols, okay? Or just kind of some kind of generic representative layout, okay? So we have examples where things are actually labeled with names and stuff, but in the beginning I have to do this kind of representative thing with generic letters here, okay? So just imagine we have a table that looks like this. Okay. So this is the generic representative layout. I'm going to start off by putting in each of these things. I've got AX and BX, and here I'm going to have total X. Over here I have total A, and here I have total B, and this is going to be the grand total. Okay, I'll also put in, AY and BY and total Y. All right, this part's okay, right? Okay, and the question might be something like, do more, or does more of X, or does, here, let's see, does more of A have X than B? Okay, does more of A have X than B? And I guess then B has X. Okay, and so to answer that question, we need what percentage of A has X versus what percentage of B has X. Okay, so this is just like your homework that we went over today, except instead of Republicans and Democrats, or what was the other, survived or died, men and women, Northeaster, I'm just replacing them with the letters A and B, okay, and X and Y. Okay, and so to answer what percentage of A has X, what would I do? I would do AX divided by total A, right? Okay, and over here I have BX divided by total B, right? Okay. And I could also ask what percentage of people have X? And that would be what? Total X divided by grand total. Okay. So each of these quantities have labels, okay? And I guess, we can get into this in a little bit. So this we often call P1. This one we often call P2. And this one we call P hat. P hat, like you wear something on your head, okay? And so we could ask, what's the difference between the percentage of A that has X and B that has X? And it would be the difference between this number and this number, right? So this one might be 70% and this is 65%. I would say 70 minus 65%, 5% difference. Okay. Okay. There's a quantity we have to calculate called the standard error. It's an ugly formula. There's nothing we can do about it. Okay? It's an ugly formula. There's nothing we can do about it. I'm going to write it out. You're going to say, what? But we'll get through it, okay? Okay, so there's a quantity that is necessary in these calculations, and it's called the standard error. And we abbreviate it SE. Okay? Okay. And it's this entire, it's a big, so I'm going to write something and everything goes inside this square root. Okay? So p hat, remember, is the total x divided by the grand total. So it's p hat, the quantity p hat, times the quantity 1 minus p hat, times 1 over total A plus 1 over total B, parentheses, everything inside square root. Can you guys read that? You can't see? Here, let me see if I can write this a little bit bigger. I need to move my head? That's the problem? Oh, my big head's in the way. Okay. I'll get that. All right. Okay. So that's the equation. All right. So p hat, and p hat you have to keep in mind is total x divided by the grand total. P hat times the quantity 1 minus p hat times 1 over total A plus 1 over total B. What does it mean? Okay. It's just what percentage of people have X. P kind of represents percentage or proportion. You can kind of think of it that way. That's why we use the letter P. So in the hat, there's a mathematical story. Huh?
That is the Y in the hat.
The hat looks like the little triangle that goes over the. I'm just writing it P hat this way. I'm just following this notational conventions. I mean, we could call it whatever we want, but just to kind of fit in with what the rest of the world uses, I'm calling it P hat, okay? Oftentimes this is actually called P hat 1 and P hat 2, but I felt like that's maybe even too many things to write. So we're just going to call it P1 and P2, okay? But to be technical, it should actually be P hat 1 and P hat 2. But I think, so if you ever, go to college and you take a real statistics course, they might use P hat 1 and P hat 2, and don't say, oh, I remember when they just use P1 and P2. Don't get mad at me. This is my disclaimer. It's really P hat 1 and P hat 2, but you want to say P1 and P2, I'm okay with that.
I'll Google you.
Huh?
I'll Google you.
So, okay. All right, so this is the standard error, and we're not done. Once you find the standard error, there's one last thing called the z-score, okay? All right, I know. We just have all these funny names, okay? The z-score, okay, and I have to write it on down here, okay, is going to be this quantity, P1 minus P2 divided by the standard error, okay? So you do P1 minus P2 first in parentheses, and then you divide by the standard error, and this is known as your z-score. And this is how we decide if the percentage point difference is a big deal and it's statistically significant, or if the percentage point difference is not a big deal and it's just something, okay? So there's all of this work just so we can get to this z-score, and this z-score tells us whether it's significant or not, okay? And the rule of thumb, and I'll write this on another page, is that if your z-score is bigger than 2, then it's significant. And if it's smaller than 2, it's not significant, okay? Or if it's, I should say the absolute value of the z-score. So if it's like more than -2, like if you're getting like -3, it's significant. But if you get like -0.5, not significant, okay? So the rule of thumb is 2. There's, depending on the situation, you might want to relax that or make it more stringent, okay? But the rule of thumb is 2, okay? So rule of thumb is z-score of 2 or more is considered significant, okay? Two or more. Okay. So you guys have all of this written down? Okay, so keep that in mind, and then we'll work through the little examples that I have here.
What is that
P hat?
No, the other one.
This one.
Yeah.
1 minus P hat. So I've got P.
minus hat.
So this is not P minus hat. It's called P hat. There's a dash there. I know it's.
They both are the same.
This is P hat, and this is 1 minus P hat.
Yeah, I know. But the P hat is the same.
The P hat is the same value.
The number you find.
Yeah, whatever this is P hat. Okay? Yeah, I mean, I don't have to put the dash in there, but then, we have words like fat, and that takes on a different meaning of something that is desirable, I guess. Huh? No. This is my sloppy handwriting, and I'm sorry that my dash over here looks more like a dot, but it's the same. It's the same. Okay, we'll work through an example. Sorry. Okay. Huh? You want me to use? You want me to just? Okay. You want me to write this? P hat? Okay. P hat. Okay. I'll do it on the next page. Okay. We'll do it on the next page. Same thing. Okay. Let's try out this problem here. Okay. I think it will work. Oh, what happened? Okay, here we go. Let's do this. Copy that. This right here. Okay. So we're going to go through all of this stuff. So these beginning ones should be easy. Okay. So this is in 2002, in the year 2002, Pew Research did a survey. They surveyed 500 people, and they said, do you support stem cell research or not? Okay. And the numbers came out like this. 210 said they support stem cell research. 290 say they didn't. And then they surveyed people again 7 years later, in 2009. And they said, do you support stem cell research, yes or no? And the answers came back 280, 220, okay? And we want to know, okay, they didn't survey all of America. They only surveyed 500 people each time. But does this indicate that had they surveyed everyone in America, they would have found something similar, where they now have more people supporting stem cell research in 2009 than they did in 2002? Or could this difference just be attributed to the fact that it was a random sample? That's what we want to know. So is this difference, we're going to get a different percentage here and here, is that difference statistically significant or not? Okay. So first off, it just says what percentage of people, percentage of people supporting stem cell research overall. Okay. So overall, they surveyed a total of 1,000 people, and overall, a total of 490 people supported stem cell research. So this quantity p hat, so I'll go ahead and do the symbol. If you want, you can use p hat, this symbol, or you can write p dash hat. It doesn't matter. Okay. So p hat would be what? 490 divided by 1,000, right? Total x divided by grand total, and then we would get 0.49. Okay? So if you want to write total x over grand total, that is p hat. So far, so good, right? That one's easy. No, you don't need to write. If you give me write down 0.49, that's good enough, okay? You don't have to. Don't get lost in the details. I want you to, huh? I mean, as long as you're doing the steps correctly, I'm okay, all right? Whether you call it total x. I mean, yeah, okay.
So the first one is always X.
Yeah, so and the generic representation, I call this x, I call this y, I call this a, and I call this b. Okay. Okay. So the percentage of people supporting stem cell research in 2002 was what? So this is P1, and we would say 210 divided by 500, and we get what? 0.42. Okay, that would be our AX over the total A. Huh? 2.8. 42.8%? Huh? It should be 42 exactly. Okay. And in 2009, so is there contention here? This is 42% exactly, right? 210 divided by 500. Okay. And then P2 is what? 280 divided by 500, I get 0.56, right? Okay, so what is the change between 2002 and 2009? I would write 0.42 minus 0.56, and I get a 14 percentage point. Okay, negative 0.14, right? A 14 percentage point difference, okay? Your answer might be positive or negative, okay? But I'm getting a 14 percentage point difference here. Okay, and so the question now is this 14 percentage point change, is this statistically significant or not? Okay. Well, we're going to find out, okay? We got to do all of that math. So you can't just say yes or no right off the bat, okay? We got to go through, huh? You got to work out the problem, right? But that's where we are, right? So this part should have all been easy, and now we're asking, is this 14 percentage point difference statistically significant or not? Yeah, it's because it's, if you started off with $100 and you ended up with 80, how much money changed? A $20 change, right? If you started off with $100 and you went up to 120, how much money changed? Also $20. So we're just looking at the absolute change here, huh?
Significant.
statistically significant or not.
So it will be always positive, that percentage.
Is this 14 percentage point difference?
Difference, I think.
Sorry. I'll write bigger. Okay.
That's easy.
Yes.
My question is, will it be always positive?
Yeah. For this class, we're just gonna make it positive. Okay. We're just gonna make it positive. Again, in a true, real college course, they would get picky about this. Okay. But here, I just want you to get the concepts and I don't want us to get lost in this positive negative business because I know that can hang us up a little bit. Okay. All right. Is this part okay? Okay. Let's do the standard error, our favorite part. Okay. All right. So I'm going to write the symbol for the standard error. I mean the formula for the standard error, and let's see if we can do this. Okay. Don't get scared. Don't get scared. All right. Okay. So I'll use the symbols this time for p hat. So I'm going to write it this way. P hat times 1 minus p hat times 1 over, I'm going to just write total A plus 1 over total B. Okay?
Question. When I say like that, I can put the multiplication sign if I want.
Yeah. So this indicates multiplication, right? Okay, and this is the standard error. All right, so let's go ahead and let's plug in our numbers. Okay, so what is p hat? What did we determine was p hat? 0.49, right? So we're gonna plug that in here, okay? And I'll show you what buttons you need to push on your calculator too, okay? Because I know that can be troublesome for people also. So we're gonna do 0.49 times 1 minus 0.49 times 1 over, what's the total A? 500 plus 1 over, what's the total B? 500 also. Okay, and so we want to get this number. Okay, so what buttons should I push on the calculator? There's going to be 2 steps here. First, we're going to do everything on the inside, and then we're going to take the square root of that. Okay, so here I'm assuming you have a scientific calculator that has at least parentheses buttons on it, okay? And if you have an old-fashioned one, you're going to have to do things the hard way. Okay, so you're going to type in 0.49, the times button, then the parentheses button, 1 minus button, 0.49, close parentheses button, times button, parentheses, 1 divided by button, 500 plus 1 divided by 500, close parentheses, equals. Okay, so if you push all the buttons in this exact sequence, you will get everything on the inside. And then, can I just take a look? I just want to make sure. You're going to hit second square root. Okay, then you're going to hit the second button. Okay, so then you hit equals. So this is line 1. And then you hit the second button. Okay. And then you're going to hit the square root, okay, which is x2 button on your calculator. It depends on what thing. Okay, and then you're going to hit the second button again. So there's 4 buttons on the second time, and you're going to hit the, answer this button. And then you're going to hit equals.
Okay, you want us to write down our equals on each first, right?
You don't have to do it. Okay, so, huh? So this gives you the standard error. So you enter these buttons exactly as you see them, and you hit equals, and then you do this second square root, second answer equals, and you're gonna get an answer. Okay. So go ahead, everybody, try this out, and we will see if we all get the same answer. Okay. So if you have your calculator, please do this. 0.49x parentheses 1 minus 0.49 parentheses times parentheses 1 divided by 500 plus 1 divided by 500 close parentheses equals.
And then you hit the second button.
Then you do second square root, second answer equals.
Oh, yeah.
What's
it?
What is the final answer?
Yeah, what is our final? Okay. Let's try this. Hang on, I'm still working. Okay. So at the end of this first one, 0.0009996. The first one. Okay. Now we're gonna do this one. Okay.
Oh, okay. I thought you wanted me to just continue.
Yeah, and then so you hit equals, and then you go through here, and then don't hit clear though. Don't hit clear. Then you're gonna get 0.0316. 0.0316.
I already got that answer.
And
then I continue second. I don't clear it. Okay, after I go
So
through
you got this one.
I got the answer.
You
0.00.
0.0009996. Okay. Don't hit clear.
Okay.
You're gonna just go ahead and push the second button, then the square root button, and then second, and then this button for the answer.
Square root.
Yes, second. So the square root's over the x square button, the x2 button. It's like on the left-hand side of the calculator. You got it. I know that calculator.
That one right there. I hit that one.
And then you're gonna hit second.
I hit square root, then that one, or that one?
You're gonna hit second.
I did that already.
And then you're gonna hit that
one.
one.
Okay.
And then second, and then answer.
Really?
Yeah. Okay, and then the answer button's down there, that button. And then you're gonna hit equals. And you get 0.0316.
Wow.
Okay? Can everyone get
All right.
0.0316, right? Yes, that is our standard error, 0.0316. Our standard error is 0.0316. Okay, so everybody, just make sure we can all do this. Okay, I know it's a bunch of buttons to push.
Can we all do it again?
Yeah, okay, go ahead, hit clear. Everybody hit clear on your calculator. And you're going to push all of these buttons in this exact thing, okay? Second answer. So there's 4 months, right? Second square root, second answer. Alright, so I'm gonna on the video, online video, I'm gonna just hit pause here and just make sure everyone's okay. Alright, so we got 0.0316, right? Okay, so that is our standard error. Okay, and then so now we're going to calculate our z-score. Okay, now what was the z-score? So we're gonna go to here. Actually, let's shoot. The z-score, okay, is P1 minus P2 over the standard error. Okay, so let's see. Let me go back a slide. And just keep this copied over. We're gonna okay, so let's get our z-score. Okay, and the z-score is P1 minus P2 divided by our standard error, okay? And we said P1 was 0.42 and P2 is 0.56, and our standard error we said was 0.0316, right? So on top, I do this part first, and I get 0.14, negative 0.14 divided by 0.0316. Okay, so 0.14 divided by 0.0316, and I get negative 4.43. Okay. And so we're just going to look, we can ignore the negative sign and we say, is this number bigger than 2? And yes, 4.4 is bigger than 2. And therefore, our difference is statistically significant. Okay. Yeah, in this class, we're just going to ignore the negative, okay? In another class, they might really care, but here we're just gonna ignore it, okay? Doesn't matter. In some cases, it does, but in our case, we're just going to say it's different, okay? And so we're going to say it's bigger than 2, right? Huh? In this one, okay? It just, huh? Just this one, okay? In my other class, statistics class that I teach, there is a difference between having a positive and negative difference, and they have different meanings. But in both cases, it's statistically significant. It's just it's statistically significant in one direction or another direction, and I think we can still understand the concept of statistical significance without getting caught up in the positive and negative direction thing, okay? So we're just going to say 4.43. Yeah, and in this class, I'm not going to stress the difference between the negative and the positive, okay? So we're going to say 4.43 is bigger than 2. Okay. 0.03. Is there a question?
How do you work out the last problem?
The very end, she got to the negative 14.
Minus the
Divided by the standard error, right? Yeah. The standard error we determined was 0.0316.
Yes.
Right. So you're going to do 0.14 divided by 0.0316. Yeah, don't worry about the negative, okay? You can ignore the negative. In our class, we can ignore the negative. You get 4.43. And we say 4.43 is bigger than 2. So the 14 percentage point difference is statistically significant, right? And where did this 14, and what is the 14 percentage point difference? I know. Point difference is significant. So I'll just have you guys write that 14 percentage point difference is significant. This is the percentage of people who supported stem cell research in 2002 was only what? 42%. And in 2009, it went up to 56%. Okay? What this is saying is that this change from 42 to 56% is statistically significant. Okay? It's not just the fact that we picked random people and we got this. This is statistically significant, right? So the text is, in 2002, only 42% of people supported stem cell research. Okay, in 2009, only 50, or I don't want to write only, we'll say 56% of people supported stem cell research. I can write. Okay, this 14 percentage point change is statistically significant.
This is our conclusion.
This is our conclusion. Okay, so our conclusion In 2002, 42% of people supported stem cell research. In 2009, 56% of people supported stem cell research. This 14% change is statistically significant. And we know it's statistically significant because we went through the work of finding the standard error, and then we found the z-score, and we found the z-score to be bigger than 2. That's our conclusion. Okay, so this part is our conclusion. Okay. Yeah, so so I think the next test or final will be more open-ended, kind of like this. Okay, and I want you guys to write. No, it's not going to be a multiple choice because it's hard to have these answer choices as like a multiple choice thing. Okay.
Can we see how it is a calculator?
Huh?
Can we see how it is a calculator?
What do you?
Can we see the formula?
Okay, yeah. So
We have to memorize it.
I'll make a note sheet online. Okay.
Okay.
That kind of captures a lot of this problem here, and that will be so it'll be closed notes, closed books, except for this one paper that I will prepare for you guys online. Okay, now of course you might complain that it doesn't contain enough or whatever, but we're gonna okay. All right, yeah. Yeah, I think it'll be short answer. Okay. I'm still figuring this out. Okay, don't stress too much. Okay. All right. Okay. Why don't we take a short break and then we'll come back.